So in this video, we'll be looking at how to generate carbenes. Last time we looked at what a carbene is. Now we'll look at how we actually make it. So first we'll be looking through how we can make carbenes through the decomposition of diazo compounds. So a diazo compound has the structure like the following. We have two nitrogens bound to a carbon with a positive charge on the central one here and a negative charge on the terminal one. Now, in this diazo compound, there exists resonance structure where you can move the electrons to the carbon like that. So you end up with a negative charge residing on your carbon. The nitrogen in the middle here still has a positive charge as it still has 4 bonds. Now, if we heat or if we irradiate this diazo compound with UV light or heat, then we will lose nitrogen. So we will be letting nitrogen leave, and we will form this reactive intermediate of our carbene. Where we have our lone pair on our carbon. Now, this carbene is obviously not stable, and you might be wondering, why do we form a carbene if it's not stable? And the answer is because this N2 bond is so favorable. This is the real driving force for the reaction to form the nitrogen gas. So the nitrogen leaves and we are left with the carbene to then react. So we'll see how carbenes react in the next video. But for now, we'll look through some examples of how we may lose our N2 from our diazo compound to see what carbenes we get out. So you may be given the following, where you are shown that you have a diazo compound and you may be asked to draw the resonance structure of that diazo compound. So you move the electrons around, making sure that you end up with the negative charge on your carbon. So now we've set up the diazo compound so that we have the lone pair on the carbon. So when the nitrogen leaves, when we irradiate this with UV light or when we heat it, we will lose the N2 and we will form our carbene. You may be presented with a problem where you are not shown the full structure of the diazo. In this case, you may just be told that you actually have N2 here. This will be more common as it's shorthand, easier to draw out. You may be asked to draw the full resonance structures, or you can just simply say that you are heating this or providing some light. You have N2 leave and you form your carbene. As so. So the second way in which we can produce carbenes is by alpha elimination. So in this situation, we have a central carbon with a hydrogen and a leaving group. So if we treat this with a base, then we can deprotonate the carbon, forming a carbanion. now we've formed our carbanion with a negative charge on the carbon. We can get our leaving group leave. When this happens, we are left with our lone pair on our carbon. As the leaving group took the electrons with it, the formal charge on this is now 0, and we have our carbene form. So if we look at an actual example of this, then we can have a molecule like the following, where here we have 2 hydrogens and we have 2 leaving groups, we have 2 chlorines. If we treat this with a strong base, such as potassium terbutoxide, we can deprotonate this carbon, forming our carbanion. Where we have a negative charge now on our carbon. When this happens, we can get our leaving group leave. This could be either of the chlorines, it doesn't matter. And we form our carbene, as shown there. The third method that we have of forming our carbenes is deprotonation of imidazolium salts. So this is where we have an imidazole, such as this here. And what we get happen is we get this reacting with an RBr group. So we have a delta plus on our R, a delta minus on our bromine. We get the lone pair of our nitrogen coming in and attacking that electrophilic R group, giving the electrons to the bromine. So now we have a nitrogen with a positive charge bound to a H, bound to an R group, still in our ring. Our bromide that we've now formed can come back in and act as a base, taking that proton. In doing so, the electrons from the proton-nitrogen bond will go to the nitrogen, giving us a neutral product, where we have an R group now attached to our nitrogen in our ring. Now, this could occur on the other side also, where we get our lone pair from our other nitrogen, attack the delta positive R group, giving our electrons to our bromine again. So this is our imidazolium salt that we formed. This will exist with a Br minus that we formed next to it as a salt. Now, this proton existing on the imidazolium ring can be deprotonated with a base. The pKa of this proton is around 21 to 24. So it's got middle acidity. So the alpha proton of a carbonyl group is around the same as this. So it's got mild acidity. So this base will take the proton will give the electrons to the carbon here, and the double bond will then move up onto the nitrogen, neutralizing our ammonium ion. In doing so, we end up with a neutral product where we have our imidazolium salt deprotonated and we have formed a carbene. So these carbenes are a very special type of carbenes known as N-heterocyclic carbenes, or NHCs. And unlike the carbenes we've come across so far, these carbenes are actually stable enough to store in a reaction flask. These N-heterocyclic carbenes are very stable compared to the carbenes we've been looking at. And they're a very special type of carbene because you can actually store them in a reaction flask and they don't react immediately like the other carbenes we've seen. You can store them and they're very useful in making catalysts. So these can bond to metals such as iridium, ruthenium, palladium, copper, and they're very useful for making catalysts in hydrogenation reactions or catalysts for Sabre, etc. They can be used for many, many reactions. Next video, we'll talk about how to generate the diazo compounds that we've seen in this video, how to actually make those diazo compounds, because there's no point in making carbenes from them if we don't know how to make them.